In this video, we're going to be taking a look at two conservation of energy problems. The first one involving the conservation of energy, some different types of energies, and also the work being done on a person. And the second one is just merely a energy transformation from one thing to another to solve for an unknown height. Now, if we take a look at the first one, we have a person diving down from 8 meters above the water, and they hit the water, and we're looking for the final velocity before they strike the water. The second part of the problem, as they sink through the water, it takes them 5 meters to come to rest. That's why the velocity equals 0 right here at the end. So if we're taking a look at the conservation of energy, and we're not including any type of work being done, which means energy is entering or leaving the system, and that there's no friction, heat, sound, or anything of that sort. We're basically saying all of the initial energy is equal to the final energy. At the very top, because they have some height off the ground, they have some gravitational potential energy, which we'll call UG, or it can be called PEG or a bunch of other things. And then we have some kinetic energy at the very end. So in this one, because it goes from the extremes, from the very top of the problem to the very bottom, we have a full conversion of gravitational potential energy into kinetic energy. So all we have to do is take those two formulas and set them equal to one another. And then after we do that, we can work out a little bit of math, and let's see what we get for that velocity. All right, so once I plugged in my numbers, I could do a couple things. We did have the mass for the diver, 50 kilograms. Turns out that you don't actually need the mass. So if you're working at a problem where you don't have the mass, there's a decent chance that it's going to cancel out in the problem anyway. So our 50 cancels out. I multiply both sides by 2 to get rid of this 1/2, and the 2 popped up in front of the 9.8 and the 8. So once I square root both sides, I got a velocity of 12.52 meters per second. Now, that's the first part of the problem. Now, when we get to the second part of the problem, we're looking for the force that the water exerts on the person in order to bring them to rest. So that we have to bring in a new formula, and that is work equals force times distance. And what we can do there is we have to find out what the work is, and we can plug in our distance of 5 meters, and then we can solve for the force. So the distance part is easy. We already know that's 5 meters. We can go ahead and write down F because that's the main unknown variable we're looking for, but we don't have a value for work. Now, what we do know is when they enter the water, that at their maximum speed, and they have a bunch of kinetic energy right over here. At the very bottom, when they hit 0 meters per second, they obviously have no kinetic energy. So if you're familiar with the concept of work, it's how much energy is being transferred either in or out of the system. In this case, out of the system. So do we know how much kinetic energy is at this specific point? We do. We could take the 1/2 m times v squared, which is the same as the 50 times 9.8 times 8. Either way, you could crank those numbers out, and you would get 3,920 joules. And I'm going to put a negative in front of that to show that that's the amount of energy that got taken out of the system. So then we can do a quick step of math, divide both sides by 5, and then our force comes out to negative 784 newtons. The negative would be showing that it's opposing the motion. Let's go ahead and take a look at our second problem. So our second problem, we're working with a person who is running at 7 meters per second, and they swing up to a certain height, and we want to solve for what that height is. Now, again, we're going to use the conservation of energy, where we have a bunch of kinetic energy, looks like, but we're at ground level, and then we obviously swing up to a different height. So this energy conversion is the exact opposite, where we're taking the kinetic energy and then setting that equal to the gravitational potential. Now, this one we don't have a mass, so as I stated earlier, there's a decent chance that we won't need it, and it's going to cancel out in our initial setup. So if we have 1 half mv squared, that equals mg, which is 9.8, times h. So it turns out our m's do cancel out. So let's go ahead and work out these numbers and see what we get. So that one didn't turn out to be too difficult. Our masses dropped out, as I said, and then we took 7 squared, which is 49, split that in half for 24.5, divided both sides by 9.8, and then that got us our final height. So when you're working out problems like these, you want to make sure you decide what kind of energies we have in the beginning and end and include those on the left and right side of the equal sign. You have to ask yourself questions like, does it have height off the ground, off the baseline height of the problem? Is it in motion? And in some particular problems, is something stretched or compressed? Basically asking if there's some elastic potential energy or not. So it turns out these ones had a pretty clean conversion, as in all of one type of motion, like gravitational, into kinetic, and then this one being the same thing, but vice versa. But then you expand it onto their formulas, work out a little bit of algebra, and then solve for that unknown variable. So I hope that was helpful to you. Thank you for watching and listening.